All right, so good morning. Welcome to class. It is May 7th. We have exactly 1 week until the AP test. So a few things coming up. Next week, we're going to have a little bit more classes than normal. So we're going to have our normal class Monday and Wednesday. Tuesday, there will be tutorials at 2 o'clock. I really suggest you show up to those tutorials. I know normally it's not as big of a deal, but we are getting really close to the AP test. Obviously, if you have an AP test during those time slots, I think most of them you shouldn't. About the only one it seems like there would be a conflict with probably would be Thursday morning. But if for any reason you have a lot of other ones around that time, just tell me. That way I'm not trying to count things off. But yeah, so we'll do the College Board released mock questions on Monday. On Wednesday, I'm going to help you make a cheat sheet. And then Thursday morning, the morning of the AP test, we're going to do a thing that's a little bit more creative, just kind of a light review, so you're not stressing yourself out, using up all of your mental energy right before the test. So I would suggest trying to go to as many of those as you can, or at least watch the videos, things like that. All right, so today we're going to look at our mock test. You're going to do corrections on your mock test. This is going to be a completely separate grade. So I want you to go through and grade yourself, compare your grade to what you get. So you're going to go here, you're going to open this rubric. So we see a few things here. One, you're going to grade yourself, and I want you to compare your grades. So your AP projected grade is your 1 out of 5 that you got on Google Classroom. Your final grade is what I put in a comment on Google Classroom on the assignment, and then your curved grade is what ended up in Skyward. All right, so you're going to go through and grade yourself and see if these were all, if they agree with what you got. Tell me if it's pretty far off, and we can kind of try to see why. All right, so we're going to open this, and obviously you can't edit this because this is my copy. So there's a few things that we can do in order to edit it. So you can go and download it. Why is the download option not showing? Whatever. So you can go and download it. You might have to open it in a new window to download it. Maybe that's what you're telling me. And you can see me in the reflection here because this is taking forever to open. So yeah, we can go here. You can download it. So download, and then it should open up. You can open this. I have Excel, so it's going to open up in Excel for me. If you have a Chromebook or a computer without Excel, you can open it in Chrome, and then you should be able to edit it. You're going to have to enable editing, obviously, because it has some simple codes in it. I am not trying to give you a virus, but all right, so we have this. Now, this is just a blank key. So what you're going to do here, it doesn't matter what your name is. You can go here. You can edit your student ID number now. So let's say your ID was 423752 or something like that. So you're going to put in your number you get, hit enter, and then we're going to see that our answers automatically appear here. So this is what you should have filled out at the top of question 1. This is going to be the answer for question 1. And you can go through this. You see question 1 is worth 1 point. You either have the answer correct here and you give yourself 1 point, not 12. You either have it correct and answer 1 point, and it will automatically go through and put a point here, and it will automatically go through and adjust your grade, so it will change your final grade there. And then let's say we get here, part B, let's imagine we didn't get part B correct. We can put a 0 there. Part C is worth 2 points, and then you can see the 2 points you can earn here. let's say we got both those 2 points, we put that in, and then let's say we just got one of those points, just one, and then everything kind of started falling apart and we started missing all the points. All right, and then we go through and then we get to the second question. This one was worth 8 points. Again, we have the amount of points. Let's say we started off really good here. We got 2. This question got everyone, so we got 0 right there. People did okay on these. Let's say we got 1 of 2. And notice a lot of these you have to have an explanation with also. So if you got higher points than I did, is probably because I disagreed with your explanation. So we go through, we got some points. So we got 4 out of 8 here. We got 5 out of 14 here. So it goes through, it calculates. So 40.9. So escape, undo that. This is the grade that showed up in a comment on the mock test. This curved grade is what showed up in your Skyward, and then this 2 out of 5. I think I adjusted this where if you got above a 40, I called that a 3. But this is the grade that you got on Google Classroom. It was 1, 2, 3, 4, 5 out of 5. So it'll automatically grade you on these. All right. So is everyone able to see that and figure that out? And if you struggle with this, if you can't figure out how to do it, just email me and I can type it in for you and I'll give you the key right here and you'll just have to do the math on your own. All right. So any questions on that, just ask them now or ask them a little bit later. Don't save. All right, so let's go through this mock test. I'm going to try to answer as much of it, and I'm going to answer each individual part of what the question could be asking for all of these. So I'm not going to go through all of these calculations because obviously these are going to be different for everyone. You can go through and check the Excel spreadsheet. It does go and solve every single one of these for you automatically. You should be able to see if you messed one of those up. So here we have part B, and this is just the person letting go at different points. So they either let go of the rope at B, C, or D. And so we can answer for any of those. So I'm not going to say B1 or 2 because it completely depends. So if we release at point B, what happens if we release at point B? We release at point B, we're kind of moving down. At this point, we're going horizontally. So what's that motion going to look like? It's going to launch kind of horizontally, right? Like it launched off the side of a table. So it is going to be half a parabola. So it's going to be a horizontal launch. And we're going to see half of a concave down parabola. So they're going to launch, they're going to the left. So yeah, it's going to launch something like this. Yeah, and all of these are some bit of a parabola. Even D, you can argue it's a parabola of 0 width. I don't know if mathematically you could say that, but point C. Now point C is here we kind of went down like this. So point C, we are going down, but we're angled up a bit right here. So we're also going to get a parabola, but launching at an angle. Parabola, concave down, launched at an angle. And then point D, I think is the most interesting one. What happens if we let go at point D? So point D is at the same height as point A. yeah, so at point D, they completely stop. So stopped, and that means they fall straight down. So they just fall straight down and into the water. All right, so each of those were 1 point. You kind of have to go and figure out which one was correct. Now, some of these are the same for everyone. So C, at what point should the person let go of the rope in order to travel the greatest horizontal distance from the shore before hitting the water? So where do they want to let go of at? There's 2 points that I was giving credit for. So obviously they're not going to let go at A. If they let go at A, they're going to just fall straight down, right? They let go at A, they just fall straight to the ground. That's called jumping directly off the edge. If they let go at D, they're just going to fall straight down. If they let go at B, they're going really fast sideways, right? This is the point where they're going the fastest. But they launch sideways and they immediately start falling down. So what we're going to see here is if we release at C, we kind of have the best of both worlds, where we're still kind of going relatively fast this way, and we're up at an angle, and so we're going to kind of launch off. So if you ever swing off of a rope swing, I don't know how many of you have ever gone off a rope swing. If you let go right at the bottom, you're just going to kind of go sideways and launch down. If you let go right here, you just fall straight down. C is nice because we have a little bit of upward velocity, so we spend more time in the air. I mean, we don't go higher than D, but we also have sideways velocity, so we can also move sideways. So it is going to be at point C. So for C, the answer is C, because we have vertical velocity to increase time in the air. And we still have some horizontal velocity to move forward. And then in our x direction, we just have displacement in the x direction is x velocity times time, right? Because we have a constant horizontal velocity in the x direction. So we want kind of a balance between horizontal velocity and time in the air. We get more time in the air by having more vertical velocity up, right? The faster we're going in the upward direction, the more time we spend in the air. And then we have to have some x velocity. So I give a point if you put point B because you're going the fastest, because that is part of the equation. But we want kind of a balance between speed in the x direction and time in the air. All right. Take that as a yes. So right now, kind of work on this as opposed to trying to go through the key specifically for your own. Yeah. Yeah, a lot of people thought point B. There is kind of an argument. I will say it kind of depends where point C is. I should have. It does have maximum speed, so it has the maximum x speed, but it just kind of goes off to the side and falls down in here. But if we get to C, we're still moving sideways and we're still going up. If you let go at point C, you're going to go kind of over here and then down, as opposed to letting go at point B. You're going to go kind of down like that. There is going to be an angle. If you could figure out the angle that you should let go at, then I can give you some bonus points for something. But yeah, I gave you a point if you put let go at point B because we have the maximum speed. But you do want to launch at some sort of an angle to go the furthest distance. All right, so the question is about the transformation of energy. So we have two cases from A to B. B to C and C to D are going to behave exactly the same. So going from A to D, what's happening? Wait, A to B, B to C, and C to D are the exact same. So A to B, we're moving down. We lose height, which means our gravitational potential energy goes down, but kinetic energy goes up. Right, we swing faster and faster. There's no friction or air resistance. Ignore air resistance and the mass and elasticity of the rope, so we don't have friction. So that means our total mechanical energy is constant, or just say mechanical energy is constant. Constant. So there's a perfect transfer of energy between gravitational potential energy and kinetic energy. And B to C and C to D are the same because the height increases. So the height goes up, so the gravitational potential energy goes up, and kinetic energy goes down because we're turning kinetic energy into gravitational potential energy, and then our total mechanical energy is going to stay constant. And again, put these into actual words and sentences. I'm not going to here because I'm going to be answering a lot of different questions to get through all of this. But yeah, this year's AP test is a lot more writing, a lot more explaining, so you really need to put these things into words. So between points A and B, my height decreases. As my height decreases, my gravitational potential energy decreases. The loss of gravitational potential energy is converted completely into kinetic energy, causing kinetic energy to go up because there is no force of friction. Because there's no air resistance, my total mechanical energy is remaining constant. Or between B and C or C to D, my height is increasing, which means my gravitational potential energy is increasing, because my kinetic energy is going down because there's no air resistance. I have a perfect transfer of kinetic energy to gravitational potential energy, keeping my total mechanical energy constant. I would suggest trying to be real precise about that. All right, so transformation of energy, and then E, the magnitude of momentum at point Z, compare with the magnitude of momentum at point B. So we're comparing momentum at B to either A, C, or D. Well, this is going to be the same for all of them. Momentum, what is momentum? How do I get momentum? And in particular, magnitude of momentum. Mass times velocity, magnitude of mass times velocity, and then notice magnitude of. So we can do mass times speed, right? Because we're looking at magnitudes. So mass times speed. So we're comparing to point B, but what's our speed at point B? Big or small? B has the maximum speed, right? So point B has the maximum speed, and that means point B has the most momentum, most magnitude of momentum, or largest magnitude of momentum. And then we can look at the other points. So points A and D are kind of easy, right? At point A, we're completely stopped. At point D, we're completely stopped. C, we're not. We're moving here, but we're moving slower than point B because we moved back up. We lost kinetic energy as that energy turned to gravitational potential energy. So A, C, and D are slower than B. Point A, C, and D are slower than point B and have less momentum. So again, total momentum is always conserved. The momentum that's being lost as the person swings back up is actually they're pulling up on the Earth itself, so they're slightly changing the velocity of the Earth. But yeah. All right, so now F. I was surprised. A lot of people got F1, but not F2. F1 was set up to make F2 easier, but a lot of people got kind of sidetracked with other things, trying to do a lot harder math. So F, an electronic force scale is attached to the rope, and the person swings from point A. So answer the following for when the person first reaches point B. So the force scale is attached to the rope, so we can know the tension of the rope. So that's kind of the point, is so we can figure out the tension of the rope. We also have the person's weight. The other thing about this is causing the centripetal acceleration of the person. Centripetal acceleration is always caused by other forces. There's never a centripetal force. It's caused by things like force of gravity, force of tension, a lot of other things. It can be caused by a normal force. Centripetal force is always caused by some other force. We never draw centripetal force on a free body diagram. Now, I never asked you to draw a free body diagram, but we can draw one here. What forces are acting on the person at the lowest point? Tension and weight. So tension holds a person up. Which one is bigger, tension or weight? And by the way, it seems like on the AP test, they are not equal here. It seems like on the AP test, they might give you the drawing and ask you to justify if it's correct. These are not equal. And by the way, I called this letter T and I called this W, right? All of your answers are in terms of T's and W's. It was to make it easier to write. And I think I even wrote tension in terms of W. So you should be able to get your final answer in terms of W. So your tension is going to be some number times W. Probably shouldn't use the letter C, like constant 1 times W, and then this is going to be constant 2 times W. So the tension is bigger than the weight because, again, we're going down, but we start moving up, right? So because we start moving up, I have to have a bigger tension pulling me up. So my tension has to be bigger in the upward direction, otherwise I'm not going to start moving upward. So in order to turn the person, the tension has to be bigger. So the answer would be tension up and weight down. Now, again, the whole point of this was to make it easy to solve the next part because it was asking for the centripetal force acting on the person in point B in terms of the quantity in part A. Well, in terms of the quantity in part. Oh, yeah, part A is the very beginning. So here we can just get the centripetal force of that net turning force, right? Centripetal force is the net turning force. Big minus small, so what minus what? Big minus small, right? Net force, we're always doing big minus small. So tension minus the weight. And it really was kind of that straightforward. So let's say our, I don't know what our numbers come out to be. Our tension is 6W and our weight is 10W. Then we literally just had to plug those numbers in that we got from A. So we could do tension. Wait, what am I saying? Put that backwards. Tension is bigger. 10W and 6W. So that would just be tension is 10W minus the weight is 6W. And for this one, we would just get 4W. So that was the goal. It would just be a simple subtraction thing. Because I could imagine them asking you a question like this on this year's AP test without having to write a whole lot. Like if there is a math question where you have to actually put a math answer in, it's probably going to be really straightforward math like that. That's easy to type. All right. Let's go. Can I turn this over? Yeah, this next part was the same for everyone, so that's going to be a little bit easier to write the answer to. The AP exam. So it really depends. There's a few options. You can either handwrite your exam, and again, the things they want you to do is they want you to write your initial. So my initials are AB. They want you to write your ID numbers. So let's say 1, 2, 3, 4, 5, 6, 7, 8. Not your student ID, your AP ID that you can find on the College Board website. So you would write that here, and then they want you to write your page number up here. So you can, if you write on paper, they want you to do these. You should have seen this video that they put up where they went through what they want you to write on the test. So if you are going to take a picture of your thing and turn it in, then you need to be doing this on a device with a camera. So if you're taking a picture, I would do it on a phone or an iPad, or if you have a laptop with a camera that you can easily take a picture of. Those would be the things to get in. If you're doing it on a computer without a camera, like my desktop right here doesn't have a camera, I would suggest typing it, because otherwise I would be trying to take a picture, somehow send it to my computer, and then somehow upload it from my computer to College Board. That would be much trickier. So it really depends on your technology situation. So we'd go over here. I think they probably want you to write it on another sheet of paper. But yeah, you would write your student ID again, or not student ID, your AP ID, 1, 2, 3, 4, 5, 6, 7, 8. You can find this on the College Board website. Write your initials again. This is page 2. And they want you to write the page, I'm assuming, because the upload order might get switched around. So it might be hard to tell which part you're on. Clearly label the part you're working on. All right, so G. The person now swings from a lower platform closer to the water. The rope is only pulled to an angle of 5 degrees. Before it was pulled to 10 degrees. But the rope is not altered in any way. Explain how the following values will change compared to when the person started at an angle of 5 degrees. So how will the time that it takes for the person to reach point B from point A change? What type of question is this, really? Yeah, it is going to be no change. This is a small angle pendulum, which makes this simple harmonic motion. And by the way, every single one of these questions I made were completely solvable without any previous parts. So there's a good chance this year's AP test is going to be kind of more like that, where you can look around a bit more. It also sounds like they're probably going to make these things really long, where they're going to try to make it where no one finishes, just so it's hard to cheat. So yeah, I kind of expect that. And then more so than other AP tests, I really feel like this one is going to be one where you can kind of look around and find parts that are easier to solve or that you can go through. All right, so it's small angle pendulum, simple harmonic motion. So we have period, or the time to complete one full cycle for the pendulum, is going to be 2 pi square root of the length of the rope divided by acceleration due to gravity, right? 2 pi square root of the length of the rope divided by acceleration due to gravity. Make sure you have your formula chart. If you don't have one, I would really suggest printing one out. It sounds like they're trying to make it where no one is going to finish as part of like the anti-cheat method, where if you try to cheat, you're going to spend so much time trying to cheat that you don't do even a tiny amount. So it sounds like that. So I mean, obviously, if you're like amazing at everything and you somehow blow through it, maybe you can. But I think they're trying to make it where you can't. I could be wrong, but that's what it sounded like. The people making the test were making it sound like is going to happen. All right, so we have the same period, so it's going to take the same time, right? Because we could imagine a full cycle would be there and back, right? That would be one full period. So going from here to here, that would be, this is half, so it'd be half of a half, so this would be 1/4 of a period. So we could say the time for the person to reach the bottom is equal to 1/4 of the period for the person to swing all the way there and back. Because we're less than 10 degrees, angles less than 10 degrees, this is simple harmonic motion. So our period is unchanged when I change my angle, as long as it's less than or equal to 10 degrees. So the time is unchanged. But what happens to the maximum speed now? We swing from a lower height. Swing from a lower initial height. And you're probably not going to be able to finish the corrections to this right now, so just kind of write down notes and you can look back through this also. But we swing from a lower height, so we have less initial gravitational potential energy. That means we have less kinetic energy at the lowest point. And less speed. So we swing from a lower height, we have less gravitational potential energy to start with, so we have less kinetic energy to end with. Kind of makes sense, right? To keep the time the same, if I go large angles, I swing really fast a large distance, right? Fast with a long distance. But if I swing through small amounts, I swing really slow over a shorter distance. And then that makes the times equal. All right, and then the little slash that I accidentally left in here, I don't know what happened there. The maximum speed is still at point B. Point B is still the lowest point. That is still the maximum speed. But the maximum speed for the smaller angle is going to be less than the maximum speed for the larger angle. All right, question 2. This was a fun one. A solid disk of unknown mass and known radius r is used as a pulley in a lab experiment, as shown in the diagram. Students want to determine the moment of inertia for the pulley. They attach a small block of mass m to the string, the other end of which is attached to the pulley and wrapped around it several times. The block of mass m is released from rest and takes a time t to fall a distance d to the floor. All right, so we go through, you'll figure out all these values here. All right, so then the first part where I'm actually grading, the time t is measured for various heights d, and the data are recorded on the following table. What quantities should be graphed to best determine the acceleration of the block? Explain your reasoning. So how are we going to get acceleration? Distance and time. So what are we probably using? Is there no kinematics gang here today? So we could do moment of inertia versus net force. The problem with that, though, is that's not what data we're given. We're given distance and time. We're not told anything about net force or moment of inertia. In fact, the whole point of this is solve for moment of inertia, so we don't know that. So based on what we're given here, distance and time, we're kind of stuck using these values. So distance and time, that's talking about kinematics. Well, which kinematic equation has distance and time and can be used to get acceleration? Well, distance and time, well, my first equation has initial and final velocity, so I can't use that. Yeah, it is going to be distance and time squared. The second equation, okay, this relies on initial velocity. Oh, well, released from rest. Okay, so this is looking good. And then the last equation has initial and final velocity, so we can't use that. So we're probably using this second equation, final position equals initial position plus initial velocity times time plus 1/2 acceleration times time squared. All right, we land on the ground. We drop from a height d. It's released from rest, so the initial velocity is 0 plus 1/2. I don't know what the acceleration is, times time squared. My acceleration is not going to be g, right? Because it's not free fall. It's being held back by the pulley itself. We have a pulley with a mass and a radius. So that pulley has rotational inertia. It does need to be turned, so we're not just in free fall. So I can subtract distance over and multiply by 2. So 2 times distance, I subtracted that over, so it's negative, is acceleration times time squared. So acceleration is going to be negative 2 times distance divided by time squared. Now, the question was, what could we be graphed in order to get acceleration? So I would put on the, so this is going to be change in y over change in x is my slope. So I would put this on my y-axis, this is my x-axis. So on my vertical, well, I'll start with horizontal. The horizontal axis should be my x, should be time squared. And then my vertical is going to be what's in my numerator. So I took a few answers for vertical. If you want this to be really correct, it would be negative 2 times distance that I would graph there. I also took just 2 times distance, and it would be okay if we got did this, we would get a positive slope, and we would just have to call the acceleration negative after the fact. I also accepted if you just put distance. So if we did distance over time squared, you would take the slope, but we would have to multiply the slope times 2 once we got it. So if we did distance divided by time squared, that would work for half the acceleration, and we would multiply that number times 2 to get our actual acceleration. So I took any of these, and we relate it to our slope is rise over run, or slope is change in y over change in x. I know acceleration, or at least magnitude of acceleration, is 2 times distance divided by time squared. And that means I'm going to put 2d on my y-axis and time squared on my x-axis. And time squared on x-axis. And the slope gives the the magnitude of acceleration. All right, and then we have C. C was the one that really surprised me that no one was getting C. Yeah, so we have the students produce a graph and calculate acceleration of the block. They then use the acceleration of the block as well as the height and time data measured to calculate the rotational inertia of the pulley. The pulley is removed from its support, and its rotational inertia is found to be less than its value. Give one explanation for this discrepancy. So the pulley is removed from the support. What might exist between the pulley and the support? Friction. Yeah, exactly. That's all this question was asking. It's friction. So there is friction between the pulley and support. And support makes the pulley hard to turn. Harder to turn, which makes it seem like that moment of inertia is larger. Right? Moment of inertia is the resistance to angular acceleration. Big moment of inertia is hard to accelerate. Small moment of inertia is easy to accelerate. So if I have a force of friction, it's making it harder for the pulley to turn. If it's harder for the pulley to turn, it makes it seem like the moment of inertia is bigger. So if we remove it from that support, and then the moment of inertia is lower, well, that's the real moment of inertia. That's the actual moment of inertia without the error of having the friction involved. So the friction makes it seem like its moment of inertia is bigger because it is harder to turn with the friction. Another way you could say is the friction provides a torque that opposes the motion. This makes it seem like the moment of inertia is larger. All right. Yeah, that was the most missed question out of everything on this one. All right, and then D and E, these are going to be.
Hi, hello, and welcome. I'm Greg Jacobs, and I'm not in my classroom right now. I am on Woodbury Forest.
Sorry about that. So D and E, I'm just going to go through these kind of real fast. These are. Yeah, so that's the advanced placement YouTube channel, and he's putting out practice questions. And I think they're made by College Board, and so those practice questions we're going to go through on Monday. That's why I had his YouTube up. All right, yeah. If you have another class, you can go. This is going to be recorded. So yeah, just check back for the rest of these. This last little bit is going to take a bit of time. All right, I'm going to start a whole new page for this last one because there's a lot of different things we want to change. So the first thing is to decrease acceleration of the block. So when we do this, I need the change and the explanation. If you just gave me a change and no explanation, I did not give you the points, all right? So we need a way to decrease the acceleration of the block. So to decrease the acceleration, we would need to do a few things. We could add friction, right? If we add friction, there's going to be a torque opposing the motion, which would slow down the acceleration. Now, the thing I have here, a lot of people are saying change mass. I was real reluctant to take the words change mass or decrease or increase mass because what mass are you talking about? The pulley or the hanging mass? So I could increase the pulley mass or radius. Right? If I increase the pulley mass or radius, then the moment of inertia for the pulley would go up. That pulley is harder to rotate, so the acceleration goes down. Make the pulley harder to spin. Either add friction or increase the radius or mass of the pulley to make this harder to spin. And then the last thing I could do is decrease the hanging mass. So a smaller mass hanging down is going to provide a smaller torque. So a smaller hanging mass, smaller torque makes this thing harder to accelerate. Or not harder to accelerate, it just accelerates less. All right, the things I'm not taking for this one is you can't change the height this drops from. If I change the height it drops from, if I drop it from a lower height, it will still have the same acceleration, it'll just have a smaller final speed. So it'll have a smaller final speed, but it'll also have a smaller time, and the acceleration will stay the same. So if you're talking about changing acceleration, you cannot talk about changing the height. That will not work to change acceleration. And then the opposite, increase acceleration, would just be the opposite. Reduce force of friction with some sort of oil, some sort of lubricant that makes this thing turn easier. So some sort of like oil or grease or something that could make the wheel turn more easily. The change in height will decrease the time, yeah. So and you can't just say change in height. To decrease the time, you would have to decrease the height. So yeah, you can do that. You can change the height for time, but not for acceleration. So we could reduce the force of friction with oil. We can decrease pulley mass or the radius. Again, this is going to make the moment of inertia go down. Smaller moment of inertia makes the pulley easier to spin. Less friction makes the pulley easier to spin, so there's going to be a bigger acceleration. Or more hanging mass. Again, if you just said more mass, I wasn't going to take that because I could decrease the pulley mass or increase the hanging mass. So you need to be specific which mass you're talking about, the pulley or the hanging mass. So more hanging mass means more torque. More torque means bigger acceleration. All right, and then times decrease time. All right, so to decrease the time to hit the ground, so this is what we're talking about. So decreasing the time, we can drop it from a lower height. Drop hanging mass from lower height. Right, lower height, less distance to fall, so less time. So I could either drop this from a lower height so it doesn't have as far to go and it's going to reach there faster. All right, if I drop it from a kilometer up, it's going to take a long time. If I drop it from a centimeter up, it's obviously going to take less time. Or I could do things to make the pulley rotate more easily. So making the pulley rotate more easily, if I want to decrease time, I want a bigger acceleration. So any of these would work here, right? Because if I increase acceleration, so if acceleration goes up, then time is going to go down, right? Bigger acceleration is going to result in a bigger final velocity. If I have a bigger final velocity, I have a bigger average velocity, it's going to get there faster. So anything I did to increase the acceleration will also decrease the time. The only additional thing I could do for time is drop from a lower height, and then the reverse for increase time. So to increase time, drop from a greater height. on spell today. Drop from a greater height or any of these. Right? If I decrease my acceleration goes down. That means my final velocity is going to go down, which means I'm going to have a smaller average speed. So more time, add friction, the pulley spins more slowly, make the pulley more massive or a bigger radius. The pulley is harder to spin, so it takes more time to spin to get there, or decrease the hanging mass is going to be the other one where we can make this smaller torque, which makes this take longer to fall, right? And then you need the explanations to get these points. All right, and then what did I call this thing? What number was that? That was, or what letter? That was D. And then E. E was the harder one here. So E is talking about either change the final angular momentum or change the final rotational energy. All right, so final angular momentum. So there's a few things we can look at here. So I'm going to go with change in angular momentum is torque times time. So this is going to be radius times force times time. It is going to pull at a 90-degree angle. Let's see. Let me make sure I'm about to say the right thing. Sorry, give me 1 second. Yeah, actually, no, I did that the other way. Yeah, so we can do that. The problem is that change in time is going to get really messy. So we could do final angular momentum is moment of inertia times final angular speed. So we have moment of inertia is going to be the moment of inertia for the pulley, final angular speed. So we're trying to get that final angular speed. So we could get, where did I calculate this? I didn't show my work. This is what I get for not showing my work. So we have, I guess I'm just going to have to draw this out. So we have this mass in here, pulling on this pulley here with moment of inertia I. So we start with a certain amount of gravitational potential energy. It's going to be mass times acceleration due to gravity times that distance d, the height h. So this turns into rotational and translational kinetic energy. So that initial gravitational potential energy is going to turn into rotational and translational kinetic energy. So we go through this. So rotational kinetic energy is 1/2 moment of inertia times angular velocity squared plus 1/2 times mass times the final speed squared. But yeah, no, we actually don't need to plug this in because we're trying to decrease. Actually, no, I do have to solve for that. So we're trying to get that final angular speed to put that in here. So that final angular speed will, tangential speed is going to be angular speed times radius So tangential speed squared is going to be angular speed squared times radius squared. So I can put this in here. Initial gravitational potential energy is 1/2 moment of inertia, final angular speed squared plus 1/2 mass times radius squared times final angular speed squared. I can factor out final angular speed squared and then divide over. Yeah, this one ends up being a mess. Moment of inertia plus 1/2 mass times radius squared. So like with a final angular speed squared, and I can take the square root of this. So this gets that gets really messy. This was definitely the hardest one. I'm sorry if you got stuck with angular momentum one. So what you need to do in order to increase the final angular momentum are a few things. So increasing the moment of inertia is going to be okay here because I can substitute this in. So moment of inertia times this square root. I would do moment of inertia squared to move that in the square root. mgd divided by 1/2 moment of inertia plus 1/2 mass times radius squared. So moment of inertia squared, and then this is a moment of inertia, mr squared. It's like dividing by moment of inertia. So moment of inertia is in the top of the square root. So I want to do something to increase my moment of inertia. Something went wrong there. Let's go with the easier ones than that. So I want to increase the distance falling. Let's go with the easy ones. So increase the distance falling. So if I want to increase the distance falling, so more distance to fall is going to result in a greater final angular speed. So that's going to be better. Let's ignore the things happening with moment of inertia because even this is still messy. I would need to go and plug some things in. Yeah, let's not worry about that. So let's just go with the easy ones. Increase the distance falling or increase the hanging mass. Oh, that's what's happening. That's decrease. Yeah, so increase the hanging mass. So bigger hanging mass is going to pull harder, bigger torque, but the time is going to drop also. So you really do need this equation for proof. Actually, this equation does work. I was looking at that wrong. We can also do things to get a increased moment of inertia, and this is for increase that final angular momentum. So we would moment of inertia squared divided by moment of inertia. Moment of inertia ends up in the numerator. So I want to do things to increase my moment of inertia. So yeah, this equation actually does work. Sorry, I didn't need to cross that out. So I could also increase the pulley mass or radius. Kind of counterintuitive, right? Because it's harder to turn this thing if it's a bigger pulley mass or radius. So you might think, oh, that's going to slow this thing down. But what's actually happening is it's increasing the amount of time it's pulling for. So it pulls on this thing for a lot longer time with the same torque. And that makes this thing get more angular momentum. So it's kind of counterintuitive that you would increase the pulley mass or radius. And we would do the opposite of these for decreasing the final angular momentum. Yeah, we already spent quite a bit of time on that. I don't want to go through more time. So if you're still confused, just ask more questions later. And then the other ones are the rotational energy of the pulley. Now, I'm going to go kind of fast to this. So change in energy, work is going to be force times distance, right? Now I can multiply this all times r. Radius times change in energy is going to be radius times force times distance, or torque times distance. So when we're trying to increase rotational energy, so I can change my torque or I can change my distance that this thing falls for, that the hanging mass falls for. This is going to be the capital D. So increase the final rotational kinetic energy. We want to do things to increase the torque, so we want to have larger hanging mass. I could also increase the pulley radius. Actually, does that work? I went through and did all this math. Yeah, it actually ends up not having an effect. I take this back. Yeah, I'm not going to change the pulley radius. That's not going to have an effect because I don't want to go through all that math again. We don't have time to go through it. But yeah, I set up the equation. If you go through and you have this one, the equation is in there. We're going to see that all that matters is the force and distance. If I change the rate, if I change anything about the pulley, that's not changing the force or distance that this mass falls for. So it needs to have a larger hanging mass or a larger distance to fall, D. So the problem with torque is radius times force. So the problem with this is that if I increase the radius of the pulley, you might think that there's more torque, but because there's also more moment of inertia, so the torque goes up, but then it's harder to turn, and then those effects end up canceling each other out. So you can't do anything to change the pulley itself. So you can't talk about changing the pulley itself, and then the opposite for decrease the final rotational kinetic energy is going to be smaller for these values. If you have questions on that last one, I can go through those individually if you email me or ask them at a later time. Otherwise, this video has already kind of gone on long enough. So again, go through, grade yourself, see if your grade is the same as the grade I gave you. You'll do that, you'll turn it in, turn in your corrected response to this. If you got something fully correct and you got the full points when you grade yourself and your grade is lining up with mine, you don't have to correct that one. And if you're still struggling the grand total for the first part is 14, but the second part is worth 8, so the grand total is 22. So, and if you type these into the spreadsheet, it will automatically do the math for you and automatically give you a grade. So hopefully you're able to get the spreadsheet working. If not, just email me and I can type them in and I'll give you all of the answers from that and I can just email it back to you. So keep doing that, keep working on that. Next week we do have the AP test on Thursday at 3 p.m. So just kind of be preparing for that. And yeah, next week we will have class on Monday. I want you to try to show up for tutorial on Tuesday at 2 p.m. if you can. And then we'll have class Wednesday and Thursday morning. The classes Wednesday and Thursday aren't going to be as rigorous going through a lot of math. It's more going to be review. Yeah, was it? Yeah, the AP test was going to be today. So you have a whole other week. I don't know if that's good or bad for you. You would pretty much be done with everything if it was today. So yeah. Well, I'm going to stop the recording to make it not be ridiculously long, but just email me if you have any questions or anything isn't working.